We're going to start with steps in Bayesian statistics. Of course, the very first step has to be well, before the prior, collect a sample, right? Collect a random sample. The next step would be to choose an appropriate prior. I do have to point out data is referred to as evidence in the textbook. But prior or conditioned on anything is evidence. I should say choose an appropriate prior with caution, because the prior that you choose may not be something that everyone's going to agree on. And some might say, well, the prior that you choose is biasing the results that you have. And that would lead to, naturally, issues. So choosing the prior must be done with the most care. The one thing that I would say that you don't have to worry about is just don't choose a non-informative prior, right? Don't choose a uniform distribution. But anything else, we've got to be careful. The next step is to compute the posterior distribution. And the last step is posterior prediction or posterior prediction check. I think some like to call it as posterior prediction modeling or predictive modeling. Any of this would work. Now, the last step. Now, if we did not have a prior, right? No prior at all, in other words, multiplying by one random sample will result in a posterior distribution, which is simply equal to the likelihood, correct? If there is no prior, if you set prior to be one, hypothetically speaking, or just to understand it easily, if that is one, posterior is the likelihood, correct? And if we use the likelihood function to estimate stuff, then we are pretty much using frequentist statistics, central limit theorem, sampling distribution, maximum likelihood estimation, all of those, correct? So this intermediate step is what's going to change the process prior. Posterior prediction check is very similar to what we did with linear models, linear regression. Once you do, for instance, y equals 2.7x plus 3, using data you estimated beta 1 hat, beta naught hat. How do we verify that this model is a good model? That a good representation of our data?
You could use your sum of squared regression.
We're going to do sum of squares. Well, we're using least squares to get to this, right? But how do we know that we are predicting things properly? What do we do usually?
Take another set of data and see if the model holds.
One, take another set of data, but we find what we call the fitted values, correct? We take the x values that we have, plug it in our model, y hat, right? Actual x, y part data, and now you have y hat equals 2.7x plus 3 that you get from the data. You can find y minus y hat, actual minus the fitted value. What is that called?
The residual.
The residual. We square that, sum of squared residuals, and if that value is small, then you have a good model that represents our data. Agreed? That last step, what we do with simple linear regression or any other type of frequentist approach, goes back to this step, the posterior prediction check. So at this step, we're going to come up with or generate data using the posterior parameters that we have to see if whatever data that we generate represents the actual data or, fits the actual data properly. Good. The same process, like frequentist approach, take this away, collect the sample, likelihood, inference, prediction, whatever. That's what we did in 2023 also. Bayesian starts, random sample, prior, changes everything, you're bringing in new information. And this last step, we call it posterior prediction check, but it is nothing but, what we do usually, such as here. Good. The next difference very consistent. The parameters are treated as random variables. In other words, when we estimate a value for a parameter, it is going to have its own distribution. Now, you may say, well, isn't that the case with a sampling distribution? What is a sampling distribution? Let's say sampling distribution of mean. What would the middle value be? The true mean, right? And
Oh yeah, those are just distributions of X bars.
right. So you have this would simply be the distribution of X bar. So mu is the true mean, and the standard error is S over square root of n. That's what we call a sampling distribution for a parameter. If I have to make an inference about that mu, I would use a confidence interval, right? What is the interpretation of the confidence interval? Let's say we come up with a 95% confidence interval for mu. And hypothetically, using this example, I'm just going to conclude it's going to be between 5 and 8. Arbitrary, completely arbitrary. But then mu will lie between 5 and 8. How would you interpret this?
If you took 100 samples of X bar you would expect 95 of those 100 samples to have their sample mean between 5 and 8.
Right? If I collected 100 different samples, then 95 out of those 100 samples will produce a mean that would fall between 5 and 8. So that is more of, the frequentist interpretation. In Bayesian, we don't call it a confidence interval, call it a credible interval. Credible interval is also known as a high density interval. So what is a high density interval or credible interval? HDI, high definition interval. In frequentist interpretation, we are treating these endpoints as fixed values, right? 5 is fixed, 8 is fixed, and I say, well, 95, if I collect 100 samples, 95 of them would produce a mean that would fall here. But just for the lower limit as lower bound, LB, UB. In Bayesian interpretation, the lower and upper bounds are not fixed, they are random. So even though the end game would look like we're finding a confidence interval, in terms of interpretation, it is not a confidence interval, rather a credible interval. What do I mean by that? Suppose I have mu and I get 95% between, say, 5 and 8, right? That is going to happen with respect to one prior, correct? Yes, no, maybe. So one posterior distribution based on one prior. So based on the choice that we have, we will say there is a 95% chance that the mean will lie between 5 and 8. We're not saying that we sample it over and over again, then 95 out of those 100 samples will produce a mean that would lie between 5 and 8. We're saying there is a 95% probability that the mean would lie between 5 and 8. Does that make sense?
Say the mean there, you mean like the true population mean?
Yeah, it's a parameter. Yeah. So the parameter here, I used mean, will lie between 5 and 8, which is why we call it as a credible interval. Based on the belief that you have, and that belief comes from the prior that you provide. So in terms of interpretation, they might look the same, but we don't come up with something called standard error in this case. We're just varying parameters to come up with a distribution, varying the prior parameters to come up with a distribution for the posterior. And if the prior is well defined, I know with 95% chance the true value will lie between 5 and 8. Does that make sense? Slight difference in interpretation. Here, we're saying 95 out of those 100 times, if you sample 95, if you sample 100 times, 95 out of those 100 times, the sample mean will fall here. But here, we're saying the true value of the mean will lie between 5 and 8, and we are 95% with a probability of 0.95. So this is a probability-based argument. Does that make sense? So this is a sampling-based argument, repeated sampling. This is a probability-based argument. So that's why, when we teach undergraduate starts, we always correct people when they say, oh, the true mean is going to lie between 5 and 8. That's not the right interpretation here. In Bayesian, we can do that, but in frequentist approach, from an intuitive perspective, this goes back to sampling, which is why we have a sampling distribution.
And I shouldn't say the only difference, but what comes to mind, a huge difference is while they're both samples of X bars, correct? Both of those.
Right. So,
but that one has a prior to it, whereas that one doesn't necessarily.
Right. And the true value will lie between mu and, 5 and 8. And this is actually for mu, not X bar. So the actual mu that you find is more likely to lie between 5 and 8. So when you compute a sampling distribution, we come up with individual samples. Each of them will give us a mean. Say you get a histogram or density curve, you get that. And theoretically, central limit theorem states that as n approaches, infinity, the true value will come here. With Bayesian, based on the data and the prior, we come up with a distribution for mu itself. Right? So we're coming up with a posterior distribution for mu. See, between the two. That posterior distribution for mu is based on the prior, the choice of prior, and the data that you bring in. That's the key difference between these two. If you change the parameters, this will change the lower and the upper bound, correct? So if you simulate your posterior prediction with, posterior distribution with different parameters, prior values, this is going to go back and forth, right? So in other words, you'll get one distribution that's between 5 and 8, another distribution that would be between 5.1 and 8.4, another distribution that would lie between 4.9 and 8.2, and you can keep on going. Does that make sense?
Those are distributions versus that, which is a sample, a random sample of
the means.
Okay.
Right? So this is a sampling distribution that we obtain from repeated sampling, and this is the distribution of the parameter itself. Does that make sense?
And we get that distribution directly from the priors.
From
With the data.
the posterior.
Okay, yeah.
Yeah, from the posterior. Good.